All right, this is going to be the note sheet on electron configuration and orbital diagrams. So I'm going to eventually annotate our periodic table, but I'm going to start with the first page here. And we're not going to do every single element in this packet. It's most important that you understand how we would do the electron configuration or orbital diagrams for elements 1 through 20. So hydrogen will be our first one. It says scientists use electron configuration and orbital diagrams to describe electrons around the atoms of elements in a shorthand way. Just like each person has an address where your mail would be sent, electrons have addresses also. So we're going to be starting with energy levels. Remember, we did the energy levels on the periodic table. Those were the numbers that were written from top to bottom along the left side of our periodic table. So for hydrogen, it only has, remember, the number of protons is going to equal the number of electrons in a neutral atom. So all the atoms we're going to be doing are neutral atoms. So right here's the proton number in this particular picture. So this would have one proton, and if it's neutral, it's going to have one electron also. When you're doing the orbital diagrams, we're going to indicate an electron by having an arrow. And it's going to be an arrow that's either pointing up or an arrow that's pointing down. Now, typically, we don't draw a full arrow. We just draw more or less kind of a half arrow. And it doesn't really matter whether you're saying this is pointing up or this is pointing down. We're just going to make one hash mark to say that this is our one electron that hydrogen would have. Each of these boxes is called an orbital. So there's the 1s orbital, the 2s orbital. The p orbital actually has three, or the p block has three orbitals. There's 3s. All of the s orbitals just have space for 2 electrons only. All the p orbitals all have 3 orbitals, so there's enough room for 6 electrons. Here's a 4s, so that would have 2 electrons. And then when you get down into these larger blocks, 3D is actually going to have 5 orbitals, which will have room for 10 electrons. So each of these individual blocks is called an orbital. And an orbital can fit a maximum of 2 electrons. So it holds a maximum of 2 electrons. So let's take a look at helium. Helium has 2 electrons. Its atomic number is 2, so it's going to have 2 electrons. So it's still going to be in the first energy level, so in that first row, there's only one orbital, so both the electrons are going to go into this 1s orbital. These electrons are going to have opposite spins. One's going to spin up and the other one's going to spin down. And this is called the Pauli exclusion principle. And this states that no 2 electrons can occupy the orbital and have the same spin. So how we're going to draw this is one electron spinning down, the other electron spinning up. Remember, electrons have negative charges. Those electrons are not going to want to get anywhere close to each other, so by spinning in opposite directions, they can exist in the same orbital. So let's go ahead and move on to lithium. Lithium has an atomic number of 3. So it has 3 protons, which means in a neutral atom, it's also going to have 3 electrons. So when we're drawing this, I'm going to start counting my electrons and just adding them in. So here's 1, 2. Now that first orbital is filled. We would say this is 1s2. There's 2 electrons in there. I've got one more electron to go, so I'm just going to say that it's spinning down. And that's all I'm going to put in that 2s orbital. So it would be 2s1. For helium, I would mark that as 2s2. And for hydrogen, it would be 2s1. So when we're writing electron configurations for atoms with multiple energy levels, scientists can abbreviate the configuration by using a bracket and using a noble gas. We're going to get into that a little bit more as we get into this, but that's what this notation is talking about. So let's go on and do some more of these smaller atoms. Next one is beryllium, which has 4 electrons. So again, my first electron I'm going to say is down, my second electron is up, and now I filled the 1s orbital, so it's going to be 1s2. Now I'm ready for the 2s orbital. Beryllium has 4 electrons. I've used 2, so here's the other 2. This one's pointing down, this one's pointing up, and now I'm out of electrons, so I've done all the electron configuration. So this is 1s2, 2s2. Now we're on to boron, which has 5 electrons. Same pattern I've been doing along, 1 down, 1 up. So that's 1s2, I filled that orbital. 2s2, 1 down, 1 up. There's our 2. Now when it comes to filling these blocks, the p block, it actually has 3 orbitals. Now electrons, because they're negative and they don't want to get next to each other, they're going to fill these orbitals one at a time until we have all 3 orbitals filled. So we've used up 1, 2, 3, 4 of our electrons. I've got 1 more left, so I'm going to put that in the first orbital. So this would be 2p1, because I have 1 electron in that p block, or p orbitals. Carbon has 6 electrons. Same sort of thing. 1 down, 1 up, 1s2, 1 down, 1 up, 2s2. So I've used 4 electrons. I've got 2 more to go. Now I'm on the p block, so I'm going to do 1, 2. They're not going to go in the same orbital. They're going to spread themselves out. So I've got the most distance between these electrons. They're not going to share an orbital. So when I finish this, it'd be 1s2, 2s2, 2p2, because I have 2 of those electrons. So this is called Hund's rule. The lowest energy configuration for an atom is one where the electrons with parallel spins will occupy separate orbitals within the orbital group. So that's why I'm putting these in one at a time. Because the electrons are negatively charged, they're going to repel each other. They won't want to be in separate orbitals, or they want to be in separate orbitals if they can be. The atom is in a lower energy state if they're in separate orbitals within the same orbital group. An orbital group would be something like the p block, or 2p. All right, going on to nitrogen, which has 7 electrons. 1 down, 1 up. Now I've filled the 1s2 orbital. 1 down, 1 up, 2s2. I have 3 more electrons, so there's 1, and there's 1. So this would be 2p3. So when you add the numbers up along the top, the 2 plus 2 plus 3, you're going to get your total number of electrons that this atom would have. It would have 7. For oxygen, we're going to have 8 electrons, so filling this one first, filling this one second. Now I've got 4 more electrons to do, so 1, 2, 3, 4. So once I've got an electron in each of these orbitals, I can go back in and start to fill up with the second electron. So this would be 2p4. On to the next page. Fluorine. So fluorine has 7 valence electrons, but 9 total electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9. So to fill this in, it'd be 1s2, 2s2, 2p5. And that would be its configuration. Now we're to neon with 10 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's all 10 electrons. I've got 2 in the 1s orbital, 2 in the 2s orbital, and 6 in the 2p6 orbital. That's all I can fit in this 2p6. Now, a shorthand way to do this is to use the noble gas configuration. We just did neon. Let's take a look at sodium. Sodium has one more electron than neon. So we know already this one's going to be filled, this is going to be filled, this is going to be filled, this is going to be filled, and this is going to be filled. When I do that, I've got 2, 4, 6, 8, 10 total electrons that I've already done. I need one more electron, and it's going to go here in the 3s orbital. So what I can do to shorthand this, instead of drawing all those up and down arrows or drawing boxes, I can say that the configuration is neon, so the same as neon, plus one electron that's in the 3s orbital. So whatever number is my outer shell of electrons, I'm going to be showing the spins for those electrons. So now I'm just going to fill in a couple of these, and I'm going to use the shortcut with using the noble gas abbreviation. So magnesium has 12 electrons, aluminum has 13, silicon has 14, phosphorus is 15, sulfur is 16, chlorine is 17, and argon has 18 electrons. So I know already that if I do neon, I'm going to be using up 10 electrons. 2, 4, 6, 8, 10. So I've used 10 electrons. I have 2 more to go. And now I'm on the 3s orbital, so down, one's up. So to fill this in, this is going to be 1s2, 2s2, 2p6, 3s2. Or I can abbreviate it in this way and just say neon plus 3s2. I'm going to let you go ahead and do the rest of these, and I'm going to move on to the next part. So here's potassium and calcium. You're going to do these the same way. Once we get into the numbers, the elements that are over atomic number 20, we would get into the D block. You're not going to be responsible for doing the D block, so these would be the last 2 that you'd have to do, the biggest elements you'd have to do a electron configuration for. So I'll go ahead and do this one. So argon is the noble gas that comes before potassium. So argon has my thing just, there we go. So argon has 18 electrons, so we can go ahead and put those in. 2, 4, 6, 8, 10, 12, 14, 16, 18. So it's got a completely filled outer third energy level. And so it's a noble gas. It doesn't want to react with anything. So once I've got argon's electron configuration down, now all I have to do is add one more electron because potassium is atomic number 19. So I have 1 electron left, and it's right there, 4s1. Same thing with calcium. I can use argon to do a shorthand. So just going to count to make sure I've got it. We're going to need 18 electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18. So when all those are filled in, it would be 18 electrons. I have 2 more because calcium has 20 electrons. So down spin, up spin. So this is going to be 4s2. So I can say it's argon plus 4s2. So after you fill the 4s and 3d orbitals, things start to get a little bit wacky and a little weird. It doesn't always go in the order that you would expect. I'm going to stop here and not continue the video. As far as filling in these bigger ones, you can go ahead and do that for yourself. It's what we've done all along. But you won't be responsible for learning how to do elements that are over element number, atomic number 20. So these are other. Now, when you're doing this on a test or you're asked to do the electron configuration of, let's say, oxygen, you're not going to have the boxes that are all labeled to do the electron configuration. So there's two different ways to think about or to remember the order of the level of filling. So one is this diagram here, where you can actually just do 1s, 2s, 3s in a column all the way down to 7. And then you drop back, and it's almost like a stair step. So we're going here. Then the next stair step is all the p orbitals. The next stair step is all the d orbitals. And then the last step is all the f orbitals. When you're filling these, you're going to follow kind of a diagonal arrow. So the first energy level you'd fill is 1s. Then you start back at the top and you do 2s. And then you'd start back at the top and do 2p, and then 3s, and then 3p, 4s. So it looks a lot like a staircase. The problem I've found is that students, when they're trying to memorize this, it can get a little bit confusing. And if you don't line these exactly up with rows and columns straight, then when you draw your lines and you're trying to follow this, it gets very confusing. I'm going to show you a better larger elements right now, and that's actually using the periodic energy levels in the order of filling. We can also look at a chart like this. This is low energy electrons, and this would be high energy electrons. And in this way, we can kind of compare the energy levels. So 1s is going to be the lowest energy level, and then 2s. Let me just go ahead and highlight these. So this is 1s, the lowest, then 2s. The 2p orbitals are going to be the next highest in energy, then 3s, then 3p, then 4s, then 3d, then 4p, and 5s. Jump back to 4d, 5p, 6s, 4f, 5d, and 6p. This is for the energy levels going from lowest to highest. So when we put this all together, and if I had taken the time to draw all those electrons, we would end up with a configuration of 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, because there's 5 orbitals and they can each hold 2, 4p6, 5s2, 4d10, 5p6, 6s2, 5d10, an F block can actually hold 14 electrons. There's 7 orbitals. And then finally, 6p6. So this is just another way to look at these ranking of energy levels as far as lowest to highest. One thing I want to draw your attention to is that this is important. This is definitions, 3 different definitions. You have to know the Hund rule, where electrons spread out within an orbital group if they can. The Aufbau principle, electrons occupy orbitals in the lowest energy level first. That's the Aufbau principle. And then the Pauli exclusion principle, where 2 electrons in the same orbital can't have the same spin. They got to be one up and one down. All right, so that's the brief electron configuration, as well as kind of annotating and using the periodic table to figure the configurations out. Table. So on the periodic table, we've already got labeled here, and in class we went ahead and we shaded in. First off, I'm going to, you can see that it says helium is part of the S block. I'm going to go ahead and just move it right over. So I'm just going to say helium is right there. So anything in the first 2 groups, group 1 and group 2, is going to be an S block. These are all going to end with the electron configuration that has S in the end. So we can kind of shade this whole part in here. This is the S block. Going to the other side of the table, we've got the P block. So everything here ends with a P orbital. So I can actually shade this whole section in here. This is the P block. The D block is next. And the D block is one of those weird ones where the energy levels kind of jump around a bit. So you can just highlight the D in the electron configurations in this periodic table all the way down through. And the last block would be the F block. And again, we can highlight all the F because everything's going to end with an F orbital. And again, you could fill those in. So what I want to show you is that we can actually use the periodic table as long as you know that the first two columns are the S block. The last group here is the P block. Then we can actually do our electron configuration using the periodic table. So to show you this, I'm just going to draw some electrons in there. Change my color to black. So here's my first electron. Here's my second electron. And I'm doing helium. So as I'm reading this, remember our energy levels are first, second, third, fourth, fifth, sixth, and seventh. And these corresponded to the number of rings the atoms had, the number of energy levels. So the first energy level, we just have two elements in it. And I've now filled that. So this is going to be, I'm going to draw this down a little bit lower, 1s2. Now there's nothing on the other side of the table, so I'm going to wrap back around, and now I'm going to do the second energy level. My first electron, my second electron. So this is going to be 2s2. I've got the second level, energy level, S block, and I've got two electrons in it, so it's 2s2. Now I'm going to go straight across the table to the second energy level, but now I'm going to be in the P block. Here's my first electron, second electron, third, fourth, fifth, sixth. So when I'm doing my electron configuration, it'd be 2p6. Now if I'm wrapping back around and I'm doing a larger element like sodium magnesium, I'm now on the third energy level, and I'm in the S block. So here's my first electron, my second electron. I filled those up, so this is going to be 3s2. I go straight across the periodic table and I put my next set of electrons in. And this would be 3p6. Now I wrap back down around the table and I'm on the fourth energy level. I've got one electron here, and let's say that this whole configuration is for calcium. I've got one electron there. I've now done 20 electrons, and my last part of the energy level is going to be 4s2. So by using the periodic table and just knowing where those blocks are, I can actually do my whole electron configuration without having the small blocks and doing all the arrows within those small blocks. When you're doing a test question, you're going to be given a test question, something like, do the electron configuration of oxygen. So let's go ahead and do that one now. Let me just go ahead and reset this. Oop, I can't because I'm recording it. So I guess I'm going to stop this video now and erase it, and then I'll come back and finish it up. All right, so if I'm doing oxygen, oxygen is right here and it's got 8 electrons. So again, following this, I can just start putting my electrons until I actually get to oxygen. So I'm going to start at the beginning. 1 electron, my second electron. So that's 1s2. There's no P block for the first energy level. So now I wrap back around to energy level number 2. 1, 2. So that's going to be 2s2. I come straight across the periodic table to the second energy level P block, and 1, 2, 3, 4. So that's going to be 2p4 will be the electron configuration for oxygen. One last thing to show you, just another way to